Hi, good morning, everybody. We still do have some available seats, so if you want to go ahead and move in and grab one. Just before we start, I have one quick administrative comment. This session has been approved, pre-qualified to support continuing education requirements for several cybersecurity certifications. If you're a member seeking attendance documentation for this session, please be sure to scan your badge at the scanner located in the back of the seating area before the conclusion of the session. Scanners will shut off 15 minutes after the session ends, so please get your badge scanned before networking with the panel participants. And because it's been pre-approved, the session has to last an hour, so have your questions ready when they open the floor. Full details on the certifications are available on the conference app and the conference website. So I'm going to take up no more of your time. I'll hand it right over to our gentleman here. Enjoy the session.
I think we got a shared screen situation here. Good. Do you want to start? All right, thanks. Sorry for the little technical difficulty there. So I'll start with just kind of introductions. So my name's David Schumann. I'm a systems engineer for SAS. So SAS is an advanced analytics company based out of Cary, North Carolina. And with me today is Dr. Donald Robinson. He's a senior vice president with MAG Aerospace. And so we wanted to get together today to present some of the things that SAS and MAG have been partnering together on, really to kind of bring operationalize analytics for ISR operations is really our focus. So we're going to start with kind of a brief introduction of each of our companies, kind of some of the capabilities that we bring to the table, and then we have some use cases, we have some videos that will show some spots where we've actually deployed analytics into the field for an ISR operation. If I start just with SAS, an introduction to SAS. So as I mentioned, based out of Cary, North Carolina. They were founded in 1970 and have been a leader in the analytics space kind of ever since their inception. And they have a lot of very large commercial applications or implementations across a variety of industries. Like one of the common places that you've probably interacted with SAS with no idea that you've interacted with SAS is when you swipe your credit card and there's a determination of whether that transaction is fraudulent or not. It's often a SAS model behind the scenes that's taking that information, scoring that transaction, and making that determination. So when you get an alert sent to your phone saying that something's fraudulent, it's likely SAS behind the scenes that's doing that. In manufacturing, predictive asset maintenance is another example where SAS has a lot of quals. So predictive asset maintenance on C-130J with Lockheed Martin. Similar use case of being able to take large volumes of data, process it very quickly, and make a decision. So on the C-130J, the platform has lots of sensors for the different pieces of equipment across the aircraft, and SAS is used to analyze that data, make determinations, if a piece of equipment's going to fail, kind of get proactive about maintenance ahead of time. One last example on the southwest border, being able to determine which vehicles should get a secondary inspection. There's a SAS model that sits there. As vehicles are crossing the border, it uses DMV data, historical information, to make a determination on which vehicles should be looked at. A secondary inspection should be conducted. And when SAS implemented that model, we saw like a 20x jump in terms of the amount of narcotics that were found in secondary vehicles when they were inspected. So what is SAS? So SAS is an analytic provider, like I said. And if you kind of look at the blue bubbles on the slide, SAS plays across what we say the entire analytical life cycle. So that really starts with data, being able to SAS is a data agnostic tool. We want to be able to pull in whatever data is available for analysis. And then, so that's the second pillar, is the analysis, being able to do machine learning, AI, statistical modeling, bringing all those capabilities to the table, and providing it also in a low-code, no-code type interface. So we want to be able to take the power of machine learning and AI and all these heavy analytical procedures and put them in the hands of subject matter experts, because that's where we see the most value, is when those types of capabilities are in the hands of people that understand the data. And then it's the deployment piece, which for our presentation today, Donald and I are going to talk through some examples. Really, we're talking about deploying to the edge. So being able to take all the analytical capabilities, being able to take them, put them on a small form factor device, directly on a sensor to make computations in real time, and provide alerts and insights on those edge, directly from that sensor. So I kind of mentioned some of SaaS's quals in the commercial space, but as we started to shift and take a lot of what we do very well in the commercial space and apply it to ISR operations, that's kind of where our partnership with MAG Aerospace came in. So best way, again, I said this already, the best way to kind of develop an application that provides true value is to pair kind of the technical capabilities with subject matter experts. And in terms of MAG, that's what they bring to the table. They're experts both in terms of the assets that are in the field, as well as the sensors, aircraft, but they also have experience on the operational front in terms of what, when you conduct analysis, what would an operator in the field, what insights would they like to have? How can we surface it to them so that it actually benefits an operation? So I'll let Donald talk a little bit more about MAG specifically, but.
Cool. Hey, good morning. My name's Donald Robinson, again, Senior Vice President of Strategic Development at MAG Aerospace. So MAG Aerospace actually got started years and years ago as a contractor at Coco ISR company. We started off with a few planes, a few turboprops flying down in South America, telling the good guys where the bad guys were. And so we've operated aircraft ever since. We've had fleets of Cessna Caravans. We did a lot in Afghanistan and Iraq and the global war on terror, but also expanded into other aircraft types, unmanned air systems. We're currently flying in most continents around the world right now, a couple 100,000 flight hours a year. And recently are about to deploy the Army's next generation ISR aircraft, Athena-R, which is moving up to a global 6,500 jet. So throughout all this experience in sort of COCO ISR, if you will, COCO meaning contractor-owned, contractor-operated. So our team are not only, building the aircraft, but also maintaining them, flying them, and actually doing the mission systems operations. So we have very first-hand experience about what really happens at the tactical edge of the field. And over time, MAG has actually grown into adjacent areas around that sort of core element of optimizing tactical decision making. And so we've expanded through acquisitions and other companies to satellite communications. So we actually work directly with Northrop and Boeing on the WGS SATCOM networks. We've worked with some special operations unit doing very specific, unique communications capabilities for them in various different places they deploy around the world. We've gotten very good in terms of how to, optimize different communication channels, not only from the tactical edge, but also back to, the mothership in one way, shape, or form. We also do a lot of training. So, for example, all Tier 1 special operators go through our training to become JTACs, or Joint Tactical Air Controllers. And so those are the people, Tier 1 special operators, your SEALs and Rangers, they go out and they're calling in fires. Through that process, though, that specific training that we do is designed around very complex decision-making scenarios. Complex authorities, complex legal challenges, complex environments, lots of sensors that need to be correlated, but the data is always imperfect. So how do you make decisions in imperfect environments? So when you pull all that together, we've got a heavy emphasis in operations, but over time we actually have a manufacturing facility down on the Space Coast where we can manufacture parts. We actually certified to 3D print aircraft parts, tactical kits. We build our own mission computer for specific size, weight, power, and computational constraints. And so when you take all of the capabilities that we have at enabling tactical decision superiority, that's where we partnered with SAS, because we saw a gap, particularly in the field of artificial intelligence. And I've I've got a long history with it. Back in back in the dark ages of grad school, I actually had to take a proficiency exam on SAS to get my master's degree. And so I've known SAS for a very long time, and one of the gaps that we saw in a lot of our operational scenarios is that there's a lot of talk about AI. I mean, it's in the news every day now. And there's this misconception that you can just sort of sprinkle the AI fairy dust on an operation and it's all going to work. And then we don't need the operators because the machines can just make the decisions, right? And that works every time, right? We just sprinkle the fairy dust on it and it's just going to work. And what ends up happening is that the tight constraints that you have, so they're the physical constraints of operations: size, weight, power, electricity, what computer's running on it, how much energy do you need to actually drive. You can't have a full bank of GPUs in the back of a turboprop aircraft. You can get a couple maybe. But then also, like, what are the operators really struggling with? And so we've seen lots of examples where there's some AI you kind of sprinkle out, and yeah, it's going to identify anomalies, and they're like, I don't care. That's not helping me with my job. So when we partnered together with SAS, the real objective is the humans always need to be in the loop, particularly in any type of targeting or strike scenario. And even in the ISR, there's a lot of ambiguity, even with the sensor data coming in. So what we wanted to focus on is how do we take the physical constraints of tactical operations, deploying in austere environments around the world with limited personnel. You can't ship 12 software developers to Mogadishu, right? It just doesn't work well. It's difficult, right? So what we wanted to do is understand the physical constraints of not only the operational environment, understand the threat environment that they're currently in, understand the physical constraints of what kit, comms, particularly in contested communications environments, are available to enable these things, and take the inherent knowledge that we have from a lot of the training that we do, and where can we partner with a company like SAS that has, I'm doing the math, right, 54 years of experience in doing statistical modeling, and really pinpoint what's going to make a difference to make the operators in the field be more scalable in their ability to make decisions, right? As we look forward to the future fight, there's a numbering issue, right? We have limited numbers of people, limited operators, limited platforms. And so what we have to do, just for our national security, is make that tactical edge more scalable. How do we do more with less? And we can do that by really taking the stuff we already have there, the sensor feeds, the communication feeds, some, relatively inexpensive innovations, and optimize it and make those operators that we deploy more scalable. So that is a big foundation of what we've done. And so when we partnered with SAS, we've picked a few areas based on real life examples and real world situations that we've been in to focus on, and we'll talk through the full life cycle. And it's not just on how do I put an algorithm in the back of an airplane, or how do I put an algorithm in the back of a ground vehicle that somebody can use and be effective, but really how do you tie it all together? How do you actually have the environments to create the models? Because there isn't a model that works, right? There's no one AI model that you can put in the South Pacific and put in the jungles of Colombia and put in the deserts of Syria, and they're going to work the same. So the ConOps is we're going to have banks of algorithms for very specific purposes, very specific sensors and very specific threats, and they would get tuned every day. So imagine as you launch your mission for the day or however long, you're also loading sort of a bank of, well, here are the algorithms for this mission. But while that's happening, how do you actually then update those for the mission tomorrow? How do I update those for the communications environment that we're going to encounter? How do I apply AI so that we can automatically switch between multiple different tactical networks in a contested comm scenario or DDIL environment? Sorry, I'm going to try not to do too much acronym soup up here. So what we've really focused on is how do we make the full life cycle of enabling tactical decision superiority work with the constraints that we have without too much wishing that we've got, $10 billion of additional investment for magical things and AI fairy dust. So that's what we've done. And so the first slide, do you want to start or do you want me to take it?
I can go.
Go for it. So
Yeah.
the first slide is sort of framing the context of all that.
Yeah, so just kind of talking through what the architecture looks like and then some of the things that Donald just hit on. I think as we look to, especially in DoD and kind of environments and operations, you need a platform that's going to be flexible and adaptable, right? Because the mission is always changing. The sensor and the data that you're collecting is always going to be changing. And there's the constraints that Donald mentioned. So, limited bandwidth. When we're trying to deploy directly on an aircraft, we have size, weight, and cooling requirements to even be able to, be airworthy and put it on the aircraft. And then connectivity kind of ties in with the bandwidth. There's lots of different situations. You could be in a completely disconnected environment. You could have some limited connectivity where assets in the field can communicate with one another, but maybe you can't reach the cloud. Or maybe you have full connectivity and you can reach to like a cloud type environment. So how do you have a solution that can accommodate all these different types of scenarios, right? And that's what we're looking to do, and that's what our solution is providing. So when we talk about the compute, the edge compute kind of engine, right? We're talking about being able to deploy on something that's very small form factor. So we're talking like 1 gigabyte of disk space, a couple gigabytes of RAM. Something. This is a dated reference, but like a Raspberry Pi, you could take the compute engine and put it on something like a Raspberry Pi. And in terms of bandwidth, you can take that edge compute node. It can run in a completely disconnected environment. So in the worst case scenario where everything's disconnected, it can still be running directly on the sensor and providing insights to the operator that's on the asset. And you'll see some of that in the demos that we show later. And then as you start to have connectivity, there's an opportunity to optimize how you use your bandwidth. All the data that's streaming through doesn't have to go and land in some external location. You make decisions about, what you send where. So take those alerts, take the key kind of components that your analytical routines are identifying, send them to the decision maker so that they can make decisions. Don't bog down all your bandwidth just streaming kind of all the data across. So you really have an opportunity to optimize what you send where to affect the operation. And then kind of the development piece. So as we start to go into this world where we have more and more AI applications, deep learning, there's heavy compute requirements to train a lot of these models, right? And so that's not going to be trained directly on edge node, but that's where on this slide, that red box where we have a development environment where you can train these models. And so, SAS is listed in that. Of course, I work for SAS, so SAS has a lot of capabilities in the analytics space, and it's something that I use every day. But you can also incorporate open source into that red box as well. So think Python models, think things that are written in C++. SAS is looking to take all the open source capability that's out there and be able to also use those and deploy those on an edge node. We know that there's a lot of value out there in the open source world, and we're looking to be able to leverage a lot of that. And then I'm going to talk a little bit more later about kind of model ops, which kind of Donald already kind of dove into, but being able to take, there's lots of different models and routines that are going to be developed in that red box. From computer vision to more the manufacturing use case where you're looking at a piece of equipment, determining how it's performing, speech to text. There's lots of different types of models that can be developed inside that red box and taken and deployed directly to the edge. But I was going to let Donald talk a little bit more kind of this concept of being able to operate in a connected environment or a disconnected environment and kind of that flexibility, what he's seen kind of from his experience and kind of the benefits of
Sure.
that.
Yeah, so as we look at the graphic there, you can see on the right-hand side, that's model development, and on the left-hand side is the actual platforms. And on those platforms, so MAG has a long history of actually maintaining the sensors and the data feeds, and so we don't make the sensors, so to speak, we just make them all work on the tactical platforms. And so there are two real concepts when we talk about applying AI at the edge that need to be accounted for in the design and requirements. And so the first one is, well, how do you connect the trained algorithms to the platform, and how often can you update them? And so if it requires like pulling out computers and putting more computers, and that may break a certification on an aircraft. We deal with things, certain certified solutions have to have special cabling in the computers, right, that doesn't burn and smoke. So what we wanted to do is actually just leveraging a lot of open source, very common open architecture concepts, containerization. I guess you can't have a good tech talk without saying Kubernetes once. But what we did is structured the whole model ops, this pairing between the algorithm development and the actual deployment of them in such a way that we can, containerize the applications, containerize the algorithms. SAS has a lot of native capabilities to basically encapsulate those models, a finished model, a trained model, so that we can use very low bandwidth connections to the field to provide those updates. And then on the flip side, because we deal a lot with, very restricted networks, like we've got a lot of expertise in deploying in classified environments and SAP environments and clouds there. So where we're partnering with SAS actually on the core infrastructure side is all the security aspects of it. So that when you have, because we've got customers that operate fully unclassified, we have international customers, we have customers that, TSSCI and SAP, and the full gamut of it. And so how can we, it would be nice, there are a lot of AI tools out there that you can go to, Amazon or Azure Cloud, but they're not available at the TSSCI level. So they look great and they make great news stories, but how do we actually enable that whole architecture of model ops with not the restricted comms from the perspective of EW and jamming and the DDIL environments, but the restricted comms that we impose upon ourselves with all of the security requirements. So we've worked a lot with SAS on the right-hand side to be able to very rapidly deploy the entire platform and training regime in classified cloud environments so that we can stand it up relatively quickly, for a mission set. It could be, weeks long, months long, years long, and then tear it down when we're done. So this concept of rapid deployability, not just at the edge, because the edge it's cool, it's the tip of the spear, right? But the back end support of it also has to work with the security constraints that we have. So, excuse me. So we focused a lot on that right-hand side. How do we actually put the security apparatus around that and connect the networks to the edge so that we can push model updates? We can basically push algorithmic mission packages is what we call it. What's your algorithmic mission package for the day? And then the other side of that is once you're at the edge, it's almost like going back to, like the 1940s in the Navy, right? A ship would go out into the Pacific and they would be alone. No comms, so they had to operate autonomously. They had to, they were basically embarked with a mission set, with an objective, and then they had to operate autonomously. And it would be great if every soldier that we have can operate autonomously in the field, but the power of our strategic advantage that we have in warfighting is our command and control apparatus to actually connect everybody. And that's what our adversaries are trying to deny. So another part of the training the algorithms is training algorithms that actually can work together. And what I mean by that, a very simple scenario. We have a SIGINT system on a ground vehicle. We have a SIGINT system in an air vehicle. Can they just share not the full raw data streams, but can I just share a finished, DF error estimation ellipse? The one platform calculates, well, I'm looking for a particular target. It appears to be in this general area. Another platform, well, it's in this area. How do they share those? So then you can mathematically combine those two results to a more accurate prediction, basic triangulation, right? But to do that, you actually have to design not only the algorithm, but the way that the communication system can cooperate with other peers and nodes so that they can perform that fusion without having to have the raw data. We had a scenario, for example, in the Pacific, so we were flying for a customer there, and they had trouble. They were trying to get all of the full motion video off the aircraft for various different mission sets down to some local areas in the Pacific Islands. And the way that they were doing it wasn't working effectively, so we redesigned the whole network, SATCOM network architecture to actually enable the full motion video feed. And so that was good. We did that. But now the next step is we don't necessarily always need the full motion video feed. Can we take snippets of it? Can we do image classification and only transmit the things that are necessary to look at? I don't need to transmit, 18 square kilometers of woods or ocean. I can transmit just a subset of that that's associated with an identified target, right? If I've got bandwidth limitations. So a big piece of how we architect the full thing is, one, don't just focus on the edge, because the edge is just the end result of what happens before it. Recognizing the security constraints we have, because we can deny comms to ourselves through all the various different classification issues. And make sure that we're designing the apparatus so that as it gets deployed to a tactical platform, it can operate with the sensors that they have locally and do everything it needs to do. But once it can connect to another platform and you transmit the right data, the algorithms can basically enrich themselves and get more accurate in the predictions and the forecastings and location estimations and classification of targets, et cetera, et cetera. And it turns out when you actually dig into the math, there's a significantly reduced amount of data that has to be transmitted if that fusion is not happening at the sensor level. If you can kind of put it in the middle and marry it with the communications layer, then you can adapt based on what bandwidth we have. In some cases we've got Starlink. It's got great bandwidth. It really is great. And sometimes we have line of sight man-A radios that have significantly less. And I'll get into that in a second, automatic switching between those for communications gateways. But I wanted to say that just in terms of like a key lesson learned, it's really looking at the full model ops, and he'll go into what really is involved in model ops, Dave will, but making sure that what we deploy is useful for those opportunistic areas where we have comms and where we can collaborate, but we have to be able to operate in fully denied environments autonomously as well. So if you design an algorithm that it requires everybody to talk to everybody all at the same time, it's not going to work. So algorithmic design and the mathematical design of what actually goes into those is critically important when we think about how our adversaries are trying to counter our use of our superior command and control.
Yeah, and I think in terms of the model ops piece, it's the automation, exactly what you're saying. Like when you have connectivity, how do you automate all that feedback to those models, right? So when we talk about models ops, we're talking about kind of the management of the models and the governance of the models, being able to organize all those models, and being able to track performance. You always want the model that's performing best deployed on those edge nodes, right? So that means you have to track performance and get feedback on how the model's performing, especially in situations you kind of mentioned, the diverse set of locations where something could be deployed, desert, jungle, etc. Like you're going to have situations where a model falls down and starts to not perform as well, and you need to have an automated flow to kind of provide that insight back to you so that you can retrain the model, deploy a different model. So how do you do that? How do you have that in an automated flow? And so kind of what SAS has built out is, an application that is a layer that is over those models that is doing just that. So looking at all those models that have been deployed, tracking which ones have been deployed to the edge, tracking all the changes that an analyst or a user kind of applies to those models, making sure that you have the best and greatest models deployed at any given time kind of on those edge nodes. And really, I think it can't be undersold like how many models you can. We have customers that have thousands or tens of thousands of models that they're using across kind of a wide variety of use cases, right? And it's a very similar thing for military operations if you think of all the potential sensors and use cases that are out there. I already kind of hit on some of those, computer vision, being able to do object detection on full motion video, any sensor that has feedback on how it's performing or the health of that particular sensor, is an opportunity to kind of analyze that data and look for failures or degradation in performance. SIGINT sensors. I mentioned speech to text. If you're collecting audio data, being able to put that into a digital format and then do something with it. Natural language processing, all the heavy hitting text analytic routines that are out there now. So each of those is a whole bucket of models, probably all in itself, right? And much less the fact that now you're looking across kind of those buckets, and you're going to have different types of algorithms deployed probably at the same time for a particular mission set. And so you want something that can go deep, obviously, in an individual area. So you want the best model for the specific use case, but you want something that's going to be able to go across those, because there's huge value in being able to fuse information, as you kind of mentioned, across those sensors. So can I take the object detection that I'm doing on full motion video? Can I take the SIGINT that I'm capturing either on the ground or in the air? And is there insights that I can get from the combination of those two that I couldn't have got from looking at either of those by themselves? And the answer is yes, there definitely is, if you can take that data and look across it and fuse it and put it together. And I think another interesting piece that we've started to see as well is, especially in this era of kind of a lot of the deep learning methods or anomaly detection methods, you don't have always the same indicators that you had in a very traditional statistics course, where you're looking at the R squared of a method to see how well it's performing, or its misclassification rate to see how often it's right or wrong. It's not as straightforward as that anymore, and you need feedback in terms of how it's performing, and that may involve some custom metrics that you're collecting that are kind of a proxy for how a model's performing. So think of in the object detection use case, maybe you're looking at pure volumes of each of the types of objects that you're looking to detect and how many you're detecting at any given time. And if you see a huge change in what's being detected, that can be a sign that you can alert a person to kind of investigate and see, is that just because we've gone to a different location and the objects that are on the ground have changed? Or is it because my model has stopped performing and I'm no longer detecting the objects that it's supposed to be detecting? So how do you have those metrics that both track performance or are a proxy for performance that can be used to alert an individual, an analyst, or somebody in the field that they need to take a closer look and investigate things further? So that's kind of what I had on the model ops piece. I think show some of the use cases. Yeah, let's show some use cases. Yeah.
So this.
Run the video. You can tell me to pause if you want.
Yeah. Okay. So here's a specific use case, and this is an actual video feed from an actual mission that we were performing. And so the circumstances around this is that we had a particular operation that we were working in a spot in the world, and it's a relatively I'm going to say unsophisticated platform that goes up and surveils different areas and looking for malicious activity. And we're looking for that malicious activity, and when it pops up, they are able to communicate with people who interdict and deal with it. And the problem that we were having is we noticed a change in the modality of the, I'll just say the adversary, or the people we were looking at, using Wi-Fi hotspots. And so they were using Wi-Fi, and what we were noticing is that certain clusters of activity would sort of pop up in places, and then we could associate that with the malicious activity that they had. The problem was when we were flying the missions, or mission systems operators, we'd go up, and you can imagine you surveil any spot in the world today, and there are hundreds and hundreds of Wi-Fi signals. And so they would go up and, just through human intuition, they would be able to look at certain areas and say, okay, this one looks suspicious, and then we would do enhanced surveillance on that and identify whether or not it was a target or not. So, one, the modality of the adversary was changing over time, right? their tactics, techniques, and procedures they were using, their utilization of communications equipment was changing. And so it was putting enhanced load on our operators in the back of the plane. So this is actually where we worked with SAS, and we said, well, here's the general problem set. We have all these Wi-Fi hotspots popping up. Some of them are associated with bad stuff, and some of them are totally normal. How do we figure that out? And so, as an example of the speed at which this can occur, really from flash to bang, was about 2 weeks. And what we looked at is, oh, okay, well, we can probably put the compute on a small edge processor that we actually had on the airplane. And we did some basic training. It's an ensemble model and what's called unsupervised learning technique. And what unsupervised learning is you feed the data into a model, and the model doesn't reason about it. It has no idea of like what is anomalous or not, because you haven't tagged, you haven't trained anything. It just looks at the data and says, this cluster of activity looks different than the rest of the clusters of activity. I can't tell you why, but I can tell you it just looks weird. And so what you'll notice on the graphic is that some of the circles that pop up are as the Wi-Fi activity is starting to be detected. The model's actually going in and looking across those hundreds and hundreds of signals and saying, these few circles look anomalous. They look different. And then we could combine that with other historical data that we had in these regions, specific SSIDs or known identifiers of Wi-Fi, and feed that into the model. So historically, it kind of knew, okay, well, this is what the pattern looked like before. This is what it looks like today. And it would highlight, again, where clusters of anomalous activity were. And then we could then overlay that with known suspicious signals. And it turns out in right there were multiple collects in an area. It highlighted it as a suspicious, an anomalous cluster, right, based on the unsupervised learning technique. We were able to overlay that with a known suspicious signal, and it basically, in a matter of seconds, the operator goes from looking at, okay, there are hundreds of tracks out there, to look right here first. You can look everywhere else, but the operator could then just zoom exactly in, perform that enhanced surveillance, and actually confirmed it was something we were looking for, and were able to deal with it. Right? So in 2 weeks, we talk about AI and AI at the edge, and sometimes at these conferences it seems like, about 2030 we'll get there, right? But in reality, we did this in 2 weeks. A couple people got together, we talked to the guy in the back of the airplane, we had some brilliant scientists from SAS and said, well, hey, here's a simple solution, and it created effect instantly. It made our operators more scalable. It made them more effective at their job. It wasn't super sophisticated DeepSeek, right, coming out of China. It wasn't OpenAI. It wasn't all these other things. It was a pretty simple, here's a mathematical technique that matches your problem set. It matches the data, and we can deploy it quickly. So in 2 weeks, we made our operators more scalable within the constraints of their platform, within the constraints of their operations, with our customers' permission. and those are the types of advancements we need to see more of at the edge. We need to see less of the big bang, we're going to go and rip and replace everything and create these new frameworks. But when we talk about the edge, there are things we can do today, and we can do them quickly, and we can create effect quickly. So where we're taking this specific example, so this is just one example of one class of algorithm. It's actually a couple algorithms using ensemble modeling. You put them together, but taking that, and then how do we take it to the next level? And so, for example, we've been working on, and Dave will talk about this, I'll try not to steal too much of his thunder, but the concept of a lot of platforms have SIGINT, right, which can pick up signals, right, from radios. And then you've also got EO, which is your cameras. And an example of how to fuse those together is not necessarily getting the right suite of sensors and cameras that work together perfectly and they automatically fuse everything. What we're doing is like putting it in between them. And so what we're doing is like pulling in the signals which can give an approximate location. Well, then can we auto clue the EO ball to basically look at and zoom in to that location and then add an image classification algorithm onto the EO, which we know in certain circumstances we're looking for like a white pickup truck or something with tracks or a large truck with a big tube on the back of it. And so can we auto slew that camera, and in a matter of 10 frames you can get an accurate image classification of what you're looking at. So now, instead of the operator physically slewing a camera, looking at something, understanding what it is, creating an annotation in the chart, you can spend 2 or 3 minutes and it will auto slew all the different areas of interest and go ahead and classify them for you, which then presents an even more enriched picture for that operator to then decide where we need to focus our attention. And so that's where now we're fusing multiple sensor operations, and then we can also fuse those sensor modalities too. We're working with how do you take 2 disconnected sensors and actually fuse their results together with a minimal bandwidth between them. So I'm not transmitting raw data streams from one to the other, and there's a mothership that's putting it all together and then redisseminating the tracks to everybody else. That doesn't work. That doesn't work in a DDIL environment. So how can I just stream, here's a particular location estimation, and here's a particular location estimation, and those algorithms, given the same data, will come up with the same result themselves, given the same data. And this is where I feel it really important. If there's anything else you get out of this talk, I would remember this quote. There's a famous statistician, as famous as statisticians can get, right? But there is a famous statistician, a guy named George Box. And my favorite quote from him was that all models are wrong. All models are wrong, but some are useful. And so when we look at the context and like this 2-week example, like I can look at it and we probably could have spent another 2 or 3 more months and found different models that we could tune and get a slightly better R-squared, get a slightly better tightness of the clustering. We could figure out, how many leaves do we want to go down in the clustering tree to like really segregate them. But at the end of the day, there's a point where it doesn't really matter. It didn't help the operator anymore. So we have to assume and know all models are wrong, but some are useful. And what's more important is how do we get the useful ones into the field faster and get that feedback and then continually refine them, instead of trying to, don't make perfect be the enemy of the good enough. So that's just an example where we are able to rapidly innovate, and we call this operational innovation. Like create this innovation in the operations itself. And yes, we have to do it at test ranges. Yes, we have to validate and training and do all the stuff we need to do. But there are little things that we can continue to push forward at the edge, at our operations, without having to wait for the rest of the apparatus to catch up to it. And that type of operational innovation is what we need to be doing more of at AI, because truly, right now, the possibilities, you can get a bunch of smart people in the room together, come up with lots of different possibilities, but we find out what's more effective when we actually talk to the people using it. So, that's an example of what we've done here for this particular mission set. It's real, it worked, continues to work, we continue to innovate. And we're now expanding this into other specific challenges that we see in our customer sets.
Yeah, and one thing to kind of just piggyback on some of what you said. I think another key point here is the integration specifically with the aircraft and taking the SAS results and putting it in the heads-up display for the pilot. Right? It's another example similar to the credit card use case where you wouldn't know that SAS is even involved in this use case, right? And that's by design. Like the most useful way is to take the results that we find and push them to the interface that the pilot is accustomed to be able to slew to the results. So another good integration kind of example. And for the clustering piece, just a small technical thing of like being able to do the clustering, that clustering algorithm can train and score in stream, which means the weights and everything that is associated with that clustering algorithm are updating as more data is being collected, which means as you go to a new environment, it can adjust without any intervention from an analyst or anybody else. So, and I can show the second video.
We got about 15 left. Do you want to take 10 extra questions?
So this was the example, kind of extending that use case from the SIGINT on the ground to incorporate the full motion video. So you saw kind of an analytical flow there that's taking in the full motion video and the SIGINT data, being able to analyze it. Now we're doing object detection directly on that FMV feed. In this case, this is unclassified, just being able to identify vehicles, things like axles on vehicles to determine the size of vehicles, tractor trailers. Just kind of an example with different feeds showing the output from that object, detection algorithm. And so now in an automated way, you're being able to get, a look at which objects are being detected, and also kind of laying the landscape of what's happening on the ground, right? As you see a lot of vehicles being detected, that gives you some insight into what's happening. And then it's about being able to take that and fuse that with the SIGINT data. So here's an example just kind of with the dashboard that's taking the SIGINT data, combining it with the FMV feed, and being able to kind of interactively go through that data. So here's an example kind of showing the path of those SIGINT sensors. There was one on the ground, one on an aircraft, circling the area that the FMV feed was kind of looking at. You can see all the devices that were detected on the ground. And so you can analyze each of those separately, and then in a little bit here on the video, it's going to be looking to correlate across those. So how can I take those and use those two feeds together? So in this case, we had kind of a specific signal of interest. We could see when that signal was the strongest. We can see the feeds associated with the FMV when that signal was at its strongest. And you can see kind of on the frames there, I kind of labeled kind of the target vehicle that had the sensor on it, and then the vehicle of interest. And you can see kind of the frames where that signal was the strongest is when that sensor is driving by the vehicle of interest. And so now we're correlating a specific signature, specific signal with the truck of interest. So now you're saying that this truck, it's easy to say that, oh, there's a white truck in the FMV feed, but how do you determine that that white truck is the white truck that you really care about? Right, and that's where the SIGINT, combining that SIGINT with the FMV feed, tells you to say, not only is that the white truck, but that's the white truck that we care about. And you've associated that signal with it. And now if you lose your FMV feed, you have another way to maintain custody of a specific, a specific asset in the field. So just a way to take those two sensor feeds, in an example and combine them together to get additional intelligence that you wouldn't have got from just the FMV feed or just the SIGINT data. Putting them together gives you an additional level of intelligence. So that's what we had for the two kind of use cases examples where we've deployed this. A framework where we can incorporate. There's numerous use cases, obviously, where you could deploy and do analysis on sensors, on assets in the field. So always looking for kind of new avenues and places where we can, deploy and get value from this. So I think from there we open up to questions if anybody has any questions.
Yes, sir.
Yeah.
Do we have any experience in acoustic data?
So we do have some experience with acoustic data, although most of it has been from like speech. So being able to take speech patterns, acoustic data from speech, and being able to associate that to a specific individual. So that's the one that I'm most familiar with. But I mean, it is another instance where I think that's one thing with the SaaS platform again is like it's a source of data. We have lots of algorithms at our disposal to do that, to analyze many different various types of data, and I think that would be a prime spot to that there would be a model that we could use and deploy. Just not something we have kind of ventured into, at least on our team specifically.
And my answer is about 15 years ago, yes, I worked on an AIoT system, and I'm also a really bad musician, and that's most of my experience with acoustic data. So, yes, sir.
Maybe not.
Oh,
You talked a lot about kind of rapid deployment of models, development of models. So I can, go into my office, I can develop a model, but getting it actually out into the fleet or into the hands of the warfighter, right? There's a qualification process, there's stakeholders involved, and they can be, very disparate depending on what the application is. So what if you talk from a big rock level, what the infrastructure that you've built has done in terms of like expediting getting those models out into the hands of the warfighter, versus the traditional path of going through risk management framework, accreditation.
Right. Okay, so the question was, I'm going to paraphrase it, getting things out quickly is often stifled by all of the process, RMF, security stuff, and validation and certification and testing. So how do we actually get it out? What do we put in place to get it out there quicker to overcome those challenges? And I'd say there are a couple things. Probably I'll start with three. I might expand. So the first one is the security apparatus, right? Cannot get away from RMF or certain the necessary risk analyses that need to be done, particularly on high-side networks. So one of the things that we've done is that if you actually look at the way you can deploy in a lot of containerized environments, you can actually sort of isolate the security boundary and then have more freedom inside that security boundary as long as you're controlling the identity and access management, data integrity, the security on the transport side, the logging, the monitoring, all the other stuff. And so the basic construct is, well, if you can encapsulate where I can deploy the algorithm and define my security boundary, and that, well, the algorithm, how it communicates outside of that is in tightly controlled environments, then that gives you freedom to basically deploy different things in there without having to like recertify them every time, right? And if you also have the chain of custody, so to speak, from the high side of the development of the finished algorithm, you can push it through that into that sort of encapsulated environment, and they go off and do their mission. You haven't really broken anything. So that's part one. So on the security side, the second piece is on the certification side, and this is where I see what we're asking the models to do. So in a lot of these use cases, what's the difference in machine learning and artificial intelligence? And I don't want to get into a philosophical argument, or we can later, but the general is that artificial intelligence is actually generally taking an action, right? Whereas machine learning is just telling you something. Here's a forecast, here's an estimation. And so in these stages, particularly where we have high consequence decisions that need to be made in the tactical field, targeting, that, what we deploy, I don't want to focus on automatically, launching a Griffin off the back of a platform. Like, not interested in that. And so the certification required to basically just enhance a display and give an operator some more information, that's a heck of a lot easier. And then let's see if that works. Let's see what the operators say. And then eventually, if we want to move down the path of actually taking actions, we can do that. I have my personal reservations about that. I always like a human in the loop. But focusing on what gets deployed in a manner that it doesn't affect the overall ConOps, it just enhances the operator's effectiveness. And let's start there. And that helps us get things out more quickly without a lot of, I'll just say, hand-wringing, if that makes sense. So those are two things I can point to. And a third is just understanding the operational ConOps of the platforms, how data gets into it. And a lot of these tactical platforms, they're very sealed, they're very specific, and so, you just have to understand those constraints and operate within them. And that's the same for whether it's a submarine or a Class 2 UAV. Other questions? Yes, ma'am. Do I have the ability to go N minus one? Okay, so if I'm going to repeat the question, I'll probably let Dave answer it. If we're continuously training a model, do we have the ability to revert back to a previous version of it if an operator determines that the training on that model they didn't like or something like that? You have the ability to revert back to a previous version. That sounds like a model ops problem.
Yeah, you can call me later about that. Call me later about that. You know, trademarked. No,
Okay.
Yeah, you can definitely do that. So being able to have, I think that's part of what the model ops provides is also kind of that version control and that ability to go from, revert back to an old model, incorporate a new version. So you can go both directions in terms of that, in terms of, which model is deployed in the field. So you can definitely do that.
I have a follow-up question to that.
Yeah.
Does the user have the ability, so in this case, an operator, have the ability to rack and stack data sources if they see that, as they absolutely know, like, there's jamming being involved here, or there's electronic warfare being involved here? Can they rack and stack data sources real time?
Rack and stack data sources.
Yeah.
Not sure I fully understand the construct, but so I'll answer the way like we're addressing that is a lot of times when you go out in the field, right? Our ConOps is that you deploy with whatever algorithmic mission package that you have for the day. And if jamming is happening and you're observing it, we're actually working on other contested communications mechanisms to basically work around errors or issues in the electromagnetic spectrum. And how we do that actually involves other models that are analyzing the spectrum. How do we move around that? And so where we get that feedback from the operator, though, is like during the mission, we're not always like retraining the algorithms while they're actually in the mission doing things. We kind of treat a day as like static. And that isn't necessarily true, but just as sort of a generalization. But we do want to get that feedback, okay, this was happening at these locations, and then being able to offload all of the raw data when we have the ability to actually get it off the aircraft, or ground vehicle, or manpack, or whatever we have deployed. And then get all that, and then get all of that data via assured comms back to the mothership, so the scientists can then comb through it and figure out, okay, they were saying this is being jammed. What of our data sources is indicating where that is, where it was originating from, what changed, and then that enables to then develop a new algorithm which goes out the next day, taking into account that feedback. And that's how we can get that feedback in a more reliable way.
Thank you.
Yes, ma'am. Did you have a question? Yes, sir.
Yes, when you were initially starting, what was your approach or level of effort to access the historical data and then sift through it and analyze it?
So we had the historical data for the first video, first use case. I think that's what you're talking about. For that particular one, we actually had a lot of historical data because we'd been flying that mission for a decade. Maybe not a decade, 9 years. But we had a lot of historical data already, and so we knew where to get it, how to get it, and it was available to us. In some cases, like the second scenario that we showed, there's a specific that's actually I don't know if this is going to answer your question, but that's actually a really big challenge, is how do I develop algorithms to train on things that I don't readily have historical data for? So an example is, let's say we want to do image classification on, the latest Chinese mobile launcher. Well, we don't have 10 of them at a range that we can run around and get a lot of companies take videos of them and train on them, right? It's just done there. So one thing we did actually in that second scenario is, we flew some artificial flight. We flew over urban areas in the United States just to collect data, to train and play with algorithms and make the video. But the other thing we did is we actually one of the other things MAG does is we write a simulation engine for EOIR training. And so I asked my sim guy, I said, look, we flew these missions over these urban areas. Can you recreate that in a simulation? He's like, yeah, in like a day, he was able to, build parking lots and buildings and stuff and have cars running around in this simulation. It was like, just like think of a gaming engine is what he was using. And then I took a video of that, of the gaming engine, and gave it to Dave and said, well, does your image classifier work on this, the simulated data? It's just as a test. And it turned out it did. So now we have a scenario where I can take a gaming engine and I can model, if I have a picture of a vehicle, well, we can create a simulated model of that and then run it through all different types of scenarios in different environments and actually drive it, and it's hiding under a bridge and it's coming out of under a bridge and all these different things, and then actually train the models on the simulated data. And again, all models are wrong, but some are useful. So here's a case where I don't have the asset to actually create the historical data track to train the image classification algorithm, but I can simulate it, and maybe that's good enough, and it's better than nothing. So that's another thing we're working on, is actually how to confidently manufacture that data.
And I think you see it also in the very structured data use case too. People focus on the computer vision use case because it's kind of a sexy use case, but there's a lot of synthetic data generation tools that SAS has to do something similar. If you wanted to simulate SIGINT data, or you wanted to simulate, you name your more structured kind of typical data source, you could still do something similar and train your model for data that if you don't have a lot of historical data for other pieces of data, you can do that too.
Do you have a question? Yes, sir.
Hi, my name is Austin Van Olst. I'm a cryptologic warfare officer, and I appreciate the work you guys have done on sensor fusion and analysis, but have you looked at other, I think there's a lot of work going on in that space. I think the intelligence community kind of is doing good things there. Have you guys looked at similar applications for like decision-making processes, command and control, basically other applications of the same kind of architecture, but outside of the sensor fusion and analysis kind of intelligence collection and targeting cycle process?
Yes. One of the areas that we're actually looking at is, I mentioned that JTAC training, where we're training special operators in complex decision environments, and how they make a decision to actually drop steel on something, right? And it has to deal with estimating, collateral damage. It has to do with, legal interpretations, classification of different this, that, and the other thing. But it truly is a human process. And there is machinery around it to help them, but it is a human process. And that's one of the things that we're actually looking at, is how can we use some of these more advanced models to get one of those operators, while they're actually performing their mission, to talk about what they're seeing, how they're seeing it, what they're seeing, and how can we actually create that audio feed with the output that they have, with the decisions, fused with whether that's the EO and the SIGINT and other things, and try and help them come up with their conclusions faster. And so it is a sensor fusion thing. And there's, the math of it's one thing like sensor fusion, just taking two things and fusing it. And you're right, the intelligence community does a fantastic job of that. But how do we take these abstract concepts of, well, here's how I'm estimating the collateral damage, and what did you see here? Well, this is a person, and it got classified as a person, but they're like, yeah, but that's one that cannot be harmed, right? And so that's one of the areas that we're exploring, is the decision processes actually in that targeting, and what would be useful for them to have presented ahead of them to make those decisions faster. So that's one specific area that we're looking at. And then there are all the other use cases of, preventative maintenance. That one's a big one. We're looking at also auto routing. So particularly, we're talking with a company that does an unmanned logistics platform. And so you've got a logistics route, you have an ISR needs. How can you sort of do auto routing between those things? What can you put on there? So there are a gazillion different use cases, but those are some of the ones I'm thinking of. I don't know if that answers your question.
Yeah, thank you.
Yes, sir.
All right, I think we can do one quick last question, and then the next presentation's coming up.
I just wanted a quick question about, what are you finding the easiest platforms to deploy your analytics to versus the hardest?
the ones I own versus the ones I don't.
Well, I mean, say someone already has like a SAP environment with a isolated system with their own Linux-based Windows and all that. What are you finding the easiest to get your data from?
From like a
original platform producing
computing
raw data.
like
Correct.
from a computing perspective.
Yes, sir.
Yeah, sorry. I was like, the easiest to deploy. God, that's a very open-ended question. I don't know if you've got a good answer to that.
No, I mean, most of our instances are kind of Linux. You're talking like Linux-based systems are kind of what we deploy on. But again, it generally comes down to the compute capabilities of it, and even in instances where there's not compute, there's an opportunity to run side by side with it with kind of a small kind of Linux-based device as well. So that's generally what we see. That's the most common, but so I guess that would be the easiest. But lots of different scenarios where we deploy in other situations as well.
And I'll say our deployment of, like when we deployed the SaaS platform, we've created kind of a cloud agnostic wrapper around it where we've got sort of the standard set of security controls, how we implement those, and we've pretty much scripted it all. So whether it's Amazon, Azure, or on-prem, like we just hook into their deployment mechanisms with the scripts. It's pretty easy. So I can deploy it to either cloud. The mechanisms between the classified clouds and unclassified clouds are generally, so we're not using some of the latest and greatest, some that we know are on the higher classification versions, so we're assured that it's going to work, the services. And so we've just basically created a sort of a wrapper with minimal connections for either security or the deployment model, and so we can do it regardless where it is.
We're looking to deploy wherever, so let me know where you want it to go.
Yeah. So I mean, we don't favor one over the other. It's just what's available. All right. Thank y'all so much.
All right,
Appreciate it.